Hello everyone, welcome to Digital Electronics and Computer Application course. I am Sudhakar Ajmera, Assistant Professor, Department of ECE, MLR Institute of Technology, Hyderabad. Today we will see universal logic gates and applications of digital logic gates as a part 2. In the previous sessions, we have seen logic gates, their types, and what are the basic logic gates, what are the special logic gates or exclusive logic gates we have discussed. And today we will see universal logic gates like NAND and NOR logic gates and all the logic gates applications as a part 2. Let us move on to overview of today's topic. We will see universal logic gates like NAND and NOR logic gates and applications of digital logic gates like AND gate applications, OR gate applications, NOR, NOT, the logic gates applications we will see. Let us move on to universal logic gates. So what are these? Universal logic gates, basically NAND and NOR are treated as universal logic gates. So the NAND gate and NOR gates are called as universal logic gates because they can perform all the three basic functions of OR, AND and NOT logic gates. In other words, I can say a universal logic gate is a logic gate that can implement any Boolean function without using another logic gates like NAND, NOR, any logic gates I can implement using NAND logic gate itself or NOR logic gate itself. So what I mean to say, I can implement AND logic gate by using only NAND logic gate, or I can implement OR logic gate by using only NAND logic gate, or any other logic gates I can implement. So I can implement NAND itself by using NAND logic gate. So there are basically AND logic gate, OR logic gate, NOT logic gate, or universal logic gates, special logic gates like XOR or XNOR logic gates are there. So all those logic gates are implemented by using NAND itself, or I can implement same AND or NOT, XOR, XNOR, NAND, NOR using NOR or NOR logic gates, I can say. So what I mean to say, any other logic gates, any Boolean function, okay, can be implemented without using any other logic gate. That is why these NAND and NOR logic gates are known as universal logic gates. Now let us move on to one by one. So first we will discuss about in detail universal logic gates as a NAND logic gate. So here the NAND logic gate is a combination of AND gate followed by a NOT logic gate, and it will produces the output 0 only when all of its input signals are high. What I mean to say here, if you observe here, NAND logic gate can be obtained by combining AND logic gate plus NOT logic gate. So what I mean to say here, the symbol of NAND logic gate is this one. For simplicity, I am taking only two inputs, A and B. These are the inputs and this is my output. Logical operator of NAND gate is this one, and expression, Boolean expression of NAND logic gate is y is equal to A dot B. So just now I said NAND logic gate can be obtained by doing inverse operation of AND gate. So what I mean to say here, I can represent NAND logic gate is equal to AND plus NOT. So here NAND logic gate symbol is this one, can be obtained by AND logic gate plus NOT logic gate. So if we combine these two gates, I can form NAND logic gate. It's a symbol of NAND logic gate. Let us see the truth table of NAND logic gate. So, truth table consists of possible number of inputs and corresponding their outputs. So, here for simplicity, I took only two inputs, let us say A and B, and Y is the output. It's a inverse operation of AND gate actually. So, with these two inputs, I will have four possibilities, four input possibilities, that is 0, 0, 0, 1, 1, 0, 1, 1. So, what it is, if you substitute this 0, 0 instead of A and B in this expression, so 0 dot 0 whole bar is 0 bar, nothing but 1. Then, if you substitute this next combination 0 and 1 into this expression A dot B whole bar, so 0 dot 1 whole bar is 0 bar, again 1. And if you substitute this 1 0 in this, A dot B whole bar is nothing but 0 bar is nothing but 1. And here last combination 1 1, if you substitute in this 1 dot 1 is 1 bar is nothing but 0. If you observe the truth table of NAND logic gate, here output is 1 when any of the input is 0, then only I can get 1 as a output, and I can get 0 output when both the inputs are 1 for 2 input NAND gate. So, it is exactly doing inverse operation of or reverse operation of AND logic gate. That is why if you add AND gate to NOT gate, I can obtain NAND logic gate. So, that is why the definition of NAND gate is a combination of AND gate followed by a NOT gate. We can observe here. And it produces low output only when all of its input signals are high, if you observe here. Now, let us move on to implementation of NAND logic gate for remaining all other logic gates. So, just now I said NAND gate is a universal logic gate. I can implement any logic gates like AND gate, OR gate, NOT gate, XOR, XNOR, NAND, NOR, all logic gates with the help of NAND logic gate. You can observe in this. So, NAND logic gate itself is a NAND logic gate. I can implement like this. And if you want AND logic gate, I can use two NAND gates like this. In series, I have to connect. So, here if you observe AB input, if you apply for this NAND logic gate, I will get A dot B whole bar. Again, on this line A dot B whole bar, on this line A dot B whole bar. And if you apply this to this NAND logic gate, it will give A dot B as per De Morgan's theorem. So, what I am going to say, not only this AND gate, I can implement OR gate. If I connect in this fashion, I can get OR gate implementation using only NAND logic gate. Here also NOR logic gate, up to here it is OR logic gate, and this one itself is NOT logic gate. I can have NOR logic gate like this. Like this, I can have NOT logic gate if I connect like this. I can also implement buffer logic gate like this. So, exclusive NOR logic gate, if I connect in this fashion, I can get it. And exclusive NOR logic gate, also I can get it like this. So, what I am going to say, any logic gates like AND logic gate or NAND logic gate or OR logic gate or NOR logic gate, NOT logic gate, buffer, exclusive OR gate, exclusive NOR gate, any other logic gates can be implemented using only NAND logic gate. If you observe here, all are NAND logic gates. So, like this, I can implement any other logic gates using NAND logic gate. Now, let us move on to one more universal logic gate, that is NOR logic gate. If you observe its definition, the NOR logic gate is a combination of an OR gate followed by a NOT logic gate. It produces the low output if at least one of its input signal is high. So let us see logical symbol of NOR logic gate is this one. For simplicity, I have taken only two inputs, A comma B, and Y is output. It will do exact inverse operation of OR gate. So Boolean expression for NOR logic gate is A plus B whole bar. Next, logical symbol we have observed, then operator, logical operator is this one. This is the logical operator of NOR logic gate. Just now I said NOR logic gate can be obtained by OR logic gate followed by NOT logic gate. So here NOR logic gate is nothing but OR gate followed by NOT logic gate if I add like this. So this, if we combine this, both of this OR plus NOT will get NOR logic gate. Let us see its truth table of NOR logic gate. So truth table consists of possible number of inputs corresponding their output combinations. So AB I am treating as an input and Y is my output. So it is nothing but complement of OR gate. So using these two inputs I will have four possibilities. They are 0 0 0 1 1 0 1 1. And if you substitute this 0 0 in this expression, 0 plus 0 whole bar is 0 bar is nothing but 1. If you substitute this 0 1 in this expression, 0 plus 1 whole bar is 1 bar is nothing but 0. Again you substitute this 1 0 in this expression, 1 plus 0 whole bar is 1 bar is nothing but 0. Now we substitute this 1 plus 1 nothing but 1 bar nothing but 0. So what did you observe? If you observe here, if it produces a low output if at least one of its input signal is high. So if you observe here, at least one of its input signal is high, then only it can produces low output. In rest of cases, when both the inputs are or all the inputs are low, then only it can produces high output, that is one output. So this is what its definition says. So it is derived, definition derived from the truth table. Let us implement this NOR logic gate for remaining all other gates as a universal logic gate. So what I said just now in the previous case, universal logic gate is a logic gate which can implement remaining all other logic gates. Here NOR logic gate can be implemented by using NOR logic gate itself, or else if I want to implement OR logic gate, I can connect in this fashion two OR logic gates in series. If I want to implement AND logic gate, I can connect like this. This is what AND logic gate. Like that I can implement NAND logic gate, NOT logic gate and buffer, exclusive OR gate and exclusive NOR gate. So that is why these NAND and NOR logic gates are universal gates, can be implemented to any other logic gates. Now let us move on to the applications of logic gates where I can apply. So digital logic gates have numerous applications in various diversified fields like computer systems and digital electronics and communication systems and data processing like I'll use this data processing as a ADC and DAC in the communication itself. Like error detection and correction codes, I'll use this logic gates for parity checking. And also in digital signal processing, I can use. Also in cryptography for encryption decryption process, I'll use encoder decoder circuits which will design with the help of logic gates. Also used in microprocessor microcontroller. Because this microprocessor microcontrollers are the sequential circuits which will be designed with the help of sequential circuits. Sequential circuits can be designed with the help of combination circuits. In that combination circuit, I can use logic gates. So, logic gates, using logic gates, I can obtain combination circuits. Using combination circuits, I can obtain sequential circuits. Sequential circuits, nothing but my IC, that is microprocessor. Using this microprocessor, I can design microcontroller. So, indirectly, I can use logic gates in the applications of microprocessor microcontroller designing. In the same way, in digital instrumentation, I can use like CROs, digital CROs I can use, or tachometers I can use. These logic gates. Like in automotive systems also I can use as a engine control unit or anti-lock braking systems. Everywhere I can use these logic gates. Not only that, in EEG machines or ECG machines, inner circuitry can be designed with the help of these logic gates. Not only that, in the industrial control systems like conveyor belt designing, I can use these logic gates. Not only that, in the DSLR cameras and image processing units, I can use these logic gates. Not only that, I can use logic gates in audio or video processing units like codecs, I'll use these logic gates. Not only that, in the networking and internet also I'll use these logic gates for designing of modems, switches, hubs. Everywhere I can use logic gates as a applications. So what I mean to say, logic gates has numerous diversified applications. Today we have discussed about universal logic gates, and applications of logic gates. In next session, we will discuss about Boolean algebra, theorems, properties, and postulates. Thank you.